So in this session, we will be now discussing about interfacing various peripherals and I/O devices using 8085 microprocessor. And based upon that, we will also be discussing some of the applications wherein we can use uh, 8085 microprocessor. So the basic purpose of a processor is to receive data from some input device, process the data, and accordingly uh, using to display that data or in the form of or store that data and so onto an output device. Right? So we have an input device, we have an output device, and in between we have the microprocessor, and it is also using it is actually interfaced with memory also. So between the input and the output devices, there can be direct communication or there can be uh, communication through some other medium. Fine. This communication between the input and output devices, with the microprocessor can also be, it can either be serial communication or it can be parallel communication. Can also be uh, an asynchronous communication or it can be a synchronous communication. And so you have communication between I/O devices and 8085. This communication is either asynchronous or synchronous, and it can also be parallel communication or it can be serial communication. So you have an I/O device, you have an input device, an output device, and you have a microprocessor in between. Now, this communication can be synchronous or asynchronous. You can have various mediums for communication as well between the input device and the microprocessor. As far as the I/O device is concerned, a microprocessor can recognize this uh, through a memory. Right? So you can have a memory-based I/O, or you can simply it can be an I/O based I/O, or you can say peripheral based I/O. So the microprocessor, this 8085, is actually able to read or identify the peripheral devices, the I/O devices, either as memory mapped or peripheral mapped I/O. Right? It's not memory based I/O, it's memory mapped. Similarly, you can have memory mapped or you can have I/O mapped I/O. Fine. Based upon the interfacing logic between the I/O device and the microprocessor. So, talking about the communication, it can be either synchronous or asynchronous. Synchronous basically means that the communication of data is not taking place at the same time. Uh, the communication of data will be at irregular intervals. While as in case of synchronous communication, the transmission of data, transmission and receiving of the data are synchronized with the same clock. Right? In asynchronous mode, this data transfer is not synchronized. And we also talked about parallel and serial communication. In parallel communication, all 8 bits of data are transmitted at once, while as in case of serial mode of data, the transmission takes place one bit at a time. And for serial input of serial communication, we have discussed, we have seen that there are a number of pins that are actually used for serial communication of data. Now, what does here peripheral, the memory mapped I/O and the I/O mapped or the peripheral mapped I/O mean? What happens in case of IO mapped IO? The IO devices are read through instructions like input, in, out, in. We have studied in instruction, we have studied out instruction. So the address of such instruction, the address of such IOs will be an 8-bit address, while as in case of memory mapped IOs, the IO devices are recognized or mapped through the memory of the microprocessor, mapped to the memory. And since they are mapped to the memory, the address of such IO devices will be identified as 16-bit. So you can have the IO devices, the data transfer between the IO device and the microprocessor using in and out instruction. So it will be simple. You can identify the IO device through 8-bit address, while as in case of memory mapped IO, the IO device will be mapped through 16-bit address. So this is some basics about the interfacing, how we can basically be able to interface. What are the different communication methods that we use for interfacing? Now, moving on, continuing with the discussion, now we'll be talking about how to interface an input device and output device. First of all, talking about interfacing output devices. Uh, we'll be first talking about, we'll take an example, and through that we'll be analyzing how to interface an output device. We here have an example of a 7-segment LED display as an output device. So this segment is basically shown here. A simple device that can be used to display numbers between 1 to 0 to 9, right? And say for example, you have different segments, and these segments can be turned on or turned off, and the interface of these devices is actually, it can be a common anode configuration or a common cathode configuration. You can see here the data lines D0 to D7 connected can be connected to different segments, either in a common anode configuration or a common cathode configuration. In either of the cases, the D0, D1, D2, D3, they are connected to the output through a NOT gate, fine. And A, B, C, D, E, F, G, they are connected to D0 to D6, while as D7 is connected to, we have D0 to D6 connected to A, B, C, D, E, F, G, and D7 connected to DP. DP is basically representing the decimal point. So say for example, we want to display 2. To display 2, A, B, G, E, and D should be on. To display 7, A, B, C should be on. Fine. So similarly to display 1, B and C should be on. To display 3, A, B, G, C, D should be on. And if you want to even display a decimal point, you want to display a decimal numbers, say for example 3.3, have point displayed, you can turn on D7. Or say for example we want to display number 7, for that ABC should be on. Now since we are connecting the D0 to D6 lines through since we are connecting these D0 to D6 to NOT gates, and we want to display number 7. ABC should be on. That means for ABC to be on, GFED should be off. For ABC to be on through a NOT gate, that means ABC, if they are connected to D0, D1 and D2, they should be actually low 0, 0, 0, while as D3, D4, D5, D6 will be 1, and D7 it's a don't care condition. Only if we want to display a decimal point, we will be turning it on, right? So to display D0 to D7, we can have a number 78 number, this is a hexadecimal number 78, that can be out to the output. Using output instruction, you can simply output this to the output device, that is in this case an LED, so that 7 is displayed on this LED. Now to see the complete configuration of this LED device, this is your complete configuration. In addition to the 7-segment LED that we have here, we have 3 more devices. That's a decoder, that 74LS138. We have an AND gate 74LS32, and we have a latch 74LS373. Why these are used? The decoder, it basically decodes the address bus, and say for example we want to output the output, and we have to using the output instruction, we want to interface the IO device. We know that this device has to be connected to a specific address, and say for example if it's any address, 0 ranging from 00 to FF, it can be any address. So using the decoder, the microprocessor basically is able to decode the address bus for generation of a specific pulse unique to this IO device. Right? It will generate a pulse unique to this particular IO device, depending upon whatever we have selected output. So we have, say for example, interface this device to a certain address, say for example 58. Fine. Then using the AND device, we can combine the address specific pulse with the control specific pulse. Now from the control signals, we have to see whether we are actually writing this onto the IO device. So both these will be high. So IO by M bar will be high, write will be high. That means they will be active actually, rather, and they will be active, and the address will be also active. We'll be specifying, we'll be combining the device address with the control signals to generate a device select pulse, right? IO select. Once we have that, for activation of the IO port, we'll be using the latch now, 74S74LS373. The LS for activation of the IO port, so that now the data bus is connected to the 7-segment LED. We will be using this latch. We have the decoder. First of all, we'll decode the address and see which address, which location we have to forward the data. Fine. Then using the AND bus, AND gate, we can combine the address with the control signals, and using the latch we can now activate the IO port for receiving the data. Whatever data we want to feed from D0 to D7, or say for example to display 7, we will be feeding 78. So display 1, we have to make sure B and C are on. That means since B and C are connected to D1 and D2, that means our output here should be D6 to D0 will be 1, 1, 1, 1, 0, 0, 1. Fine. So you can see which number it is in hexadecimal number. Accordingly, you can output that to the 7-segment LED. This is interfacing the output device. Similarly, we can interface the input device. We'll be taking a specific example of a data input from DIP switch. So except for some minor differences in the bus signal and the component differences, the interfacing of output device is similar to that of output devices. This is the circuit diagram shown here for interfacing DIP switch. Now from these switches, we'll be actually receiving the data. Instead of transferring the data, we'll be receiving the data from these input switches. And rest of the devices, the decoder will be same, because we have to still decode which address the output IO device is connected to. AND bus will be used, AND gate will be used to see. Now instead of writing the data, we are reading the data. So instead of having the control signal read, control pin write connected here, will be have the control pin read connected here. That will be the minor difference here. So that control signal will be clubbed with the decoder to enable the buffer to receive the data We do not have the latch here. Latch basically makes sure that the data is transferred from the data bus to the output device. The buffer makes sure that the data is received from the IO device onto the data bus. There are minor variations between interfacing input devices and interfacing the output devices. So you can have a number of components. You have to use a number of components, and each component has its specific role. You have to use decoders, you have to use AND gate, you have to use latch, you have to use buffers for interfacing IO devices. Uh, Similarly, we can interface ADCs and DACs. So without going into the details, this is the circuit diagram for interfacing DACs. You can see again that decoder is used for multiplexing, for combining the various address lines with this control signals, and then you can, since this is DAC, that means this is a digital to analog converter. So digital input will be received from the microprocessor. So this is almost similar to saying like we are interfacing an IO device. So the data bus will be used to forward the out data onto the DAC. You have here a DAC, an AD7522 DA converter. You have studied different DACs, R2R, and you have also studied ADCs like specific approximation method. So again, using decoders, using different gates, you'll be interfacing different types of DACs with microprocessor for receiving the data from the data bus. Fine. And similarly, you can interface the ADC. ADC will be used for receiving the data. So you may have an analog input that will be converted to a digital output, and that digital output has to be fed to the microprocessor, and so the data bus D0 to D7 will here receive the input from the ADC, and buffers will be used for receiving the data. And again, you have encoders here to multiplex for decoding the address line, and also for combining them with the status signals of the device. So this is about interfacing various IO devices. I'm not going into the details of the interfacing because we are actually running out of time. So this is about interfacing device. Interfacing. We also already studied how to different types of uh, interfacing in through pole IO, how the IO devices can be interfaced, different techniques of interfacing, and using pole IO, memory mapped IO, or interrupts DMA. We have already studied that. We can input the you can input you can interface an input device, you can interface an output device. An input device can be a keyboard, a mouse. You can interface an output device that is used for display. Fine. So these are actually commonly used input devices. The microprocessor 8085 that you use in a lab experiment is interfaced with a keyboard, and that is an input device, and it is also interfaced with an output device, a display segment that basically displays the result. So these two devices are used in a lab, in a kit, for practical demonstration. So you should be able to you should know how the keyboard and a 7-segment LED is interfaced. We have only talked about while seeing these well this this is the representation of interfacing 7-segment LED with the microprocessor. We have only seen the hardware of this system. Regarding the software, software will be actually a program that you have to embed into the microprocessor. Right? So as I've been saying to you from beginning, that there will be specific address lines that will be meant for various purposes. So there will be some address lines that will be used for interfacing the digital the IO devices, the LEDs and the keyboards, and they will be reserved for them. So you cannot access those address lines, address memory locations, sorry. And on those memory locations, you'll have written the programs for interfacing this LED or interfacing a keyboard. Now these will consist of simple commands like input, in and out, and for interfacing the IO devices. So without um, going further into any details, since we are actually out of time, so this might be our last lecture. So we'll stop here, and hopefully I'll be forwarding some 2 to 3 programs more so that you'll be able to do them and simulate them using the simulator that we have discussed.